Hi friends, welcome to SPJK Technosoft, your one-stop training and education platform. In this video you are going to learn about toroid magnetic field. This topic is from CBSE 10+2 Physics Syllbus Chapter 4, Moving Charges and Magnetism. Topics covered in this video are, what is meant by toroid? How do you calculate the magnetic field of a toroid? Is the magnetic field inside a toroid uniform? Why magnetic field outside a solenoid is zero. In this channel you are going to learn physics from our subject matter expert Mr. Phani Kumar, who is having more than 15 years of experience in teaching physics. For engineering, diploma, CBSE 10+2 students and other competitive exams like NEET, IIT, EMCET, ECET, CBSE 10+2 exams. You will receive more updated videos on CBSE and other competitive exams syllabus videos, so do subscribe our channel and press the bell icon to get the new videos at your fingertips. Happy learning, viewers.
In this video we are going to discuss about toroid. Let us start. Toroid. What is toroid? Toroid, simply we can define a toroid as a endless solenoid. An endless solenoid can be defined as toroid. What is meaning of an endless solenoid? We know that solenoid nothing but a current carrying wire. It is wound in a spring shape. Now this can be molded in a circular shape. If you make it in a circular shape, then it looks like this. Here. Then this is called as, actually we call it as toroid, an endless solenoid, because the starting point is here, again here, and we can treat it as a endless solenoid. Now if you can for a simple diagram, here they are using like this. Here this is toroid. In case of a toroid, again we need to calculate magnetic field strength. The expression for the magnetic field of a toroid, that is mu naught into n into I. The same expression which we have used for solenoid, but here the value of small n will vary. Small n is called a number of turns per unit length. Number of turns per unit length, that is small n. Actually here small n value, let us discuss. Let us prove the expression for toroid, then you can understand what is small n and its expression. For this, please say I am drawing here a toroid. Here I am drawing a toroid here, and let us consider here current wire is wounded like this. Around here, this is the solenoid. Now to derive expression for the magnetic field strength, we are dividing into three regions. First of all, inside the toroid, outside the toroid, within the toroid. Inside, outside, and within the toroid. Now coming to the, first of all, let us discuss about inside the toroid. To calculate magnetic field strength inside the toroid, please see here I am taking a dotted line. Please, this dotted line, this is Amperian loop. Amperian loop. Please see this Amperian loop, because these are the currents flowing in the wire. Please see here, currents are flowing here. This is the wire inside here. But the Amperian loop, if you take this Amperian loop which doesn't enclose any current, means here current enclosed. Current enclosed by the Amperian loop will be equals to 0. Where we are calculating? Inside we are calculating. Inside of a toroid, I have taken an Amperian loop in which the current enclosed is 0. Whenever current enclosed is 0, if you apply Ampere's law, integral b bar dot dl is equals mu naught into I, then it will become 0. Means inside the toroid there is no magnetic field. Easily we can understand. This is the first region we have calculated. Means in the first region means inside the toroid there is no magnetic field. Easy to remember. Now coming to the outside region, let us discuss about outside region here. here. Outside means in third region. In the third region, if you are going to calculate a outside toroid. Outside toroid. Now outside toroid, what will happen here? Please observe this here. If you observe the current carrying wire here, please see the dotted points and please observe these crossed lines here. Crossed lines means in these crossed lines and dotted lines. Please observe here. Every cross here, this point, actually this represents into the plane, currents flowing into the plane, and dot represents out of the plane, currents are flowing out of the plane. By the combination of these two, please see every dot and every cross, a combination of two, inside and outside the currents are flowing, means what we understand, the net current will be zero. Net current will be zero. Whenever the net current is zero, again according to Ampere's rule, integral b bar dot dl is equals to, it will become zero. Means outside of the toroid also magnetic field is zero. No need to calculate outside also. Means easy to remember. For in case of a toroid, inside magnetic field zero, outside also magnetic field zero. Only magnetic field is generated in the second region only. Second region means within the toroid. Let us verify within the toroid what is the strength of the magnetic field. Please see. Now to calculate inside the toroid, please see. Just I am taking once again we are drawing a diagram here. Here. Already we have calculated outside, inside and outside where B is equal to 0. Now we want to calculate in the second region. For this here, I am taking an Amperian loop here. This is. Now the dotted line represents Amperian loop. Now please observe Amperian loop. How much current it encloses? Please observe here. If you take a current carrying wire here, like this, current carrying wire, it encloses only inside the currents which are flowing into the plane or out of the plane. Into the plane or out of the plane. Actually here these are we are representing with dotted lines. Please observe here. Dotted lines means it represents into the plane. Whenever currents are representing into the plane, we have to take crosses here. They are representing into the plane. Here they are representing dots. Here means the Amperian loop encloses only one direction of the currents. That's why the current flowing here whatever the current flowing which is not equal to 0, then that is equals to not equal to 0 and it is equals to I value. Now you can apply integral b bar dot dl is equals to mu naught into I. Again here b and dl are in parallel to each other. B bar is parallel to dl and theta equals to 0 degrees. Then if you take theta equals to according to the dot product, you can write integral b into dl is equals to mu naught into I, because we know the dot product formula a bar dot b bar is equal to ab cos theta. I am writing b into dl, cos 0 is equals to 1. B is constant, I am taking out of the integration. Now b is equals to mu naught into I by integral dl. Please see, integral dl means where on the Amperian loop, if you take a small element dl element on the Amperian loop here, dl represents, suppose if I have taken the radius is r here, then it will be equals to circumference of the Amperian loop. That is for a circular shape it can be written as 2 pi r. B is equals to means where you can write integral dl is equals to 2 pi r. It shows the total length of the Amperian loop. Integral b bar is for n number of turns you can multiply with n here. For n number of turns you can multiply with n. That is equals to b is equals to mu naught into I by 2 pi r into n. Now finally we can conclude this. B is equals to, please see here, P is equals to mu naught into, within the brackets we are writing capital N by 2 pi r into I. Now what is capital N into 2 pi r? That is we are representing with small I. That is we are representing with small I. Again we can understand that here small n. What is difference between small n and capital N? You see that capital N means total number of turns. Total number of turns in the toroid, whereas small n represents capital N by 2 pi r, which represents number of turns per unit length. Number of turns per unit length. This is the expression for magnetic field strength due to a toroid. The same expression you can observe in case of solenoid also, but the n value will vary. Here n value is capital N by, we have taken capital L, that is number of turns per length of the solenoid. Here these toroids also we are using in case of electromagnets in industries. Finally we can conclude in case of solenoid. Solenoid capital B is equals to mu naught n into I, where small n stands for capital N by L. Here L is length of the solenoid. In case of toroid again capital B is equals to mu naught into Ni, where n is equals to capital N by 2 pi r. because toroid is in a circular shape, we can take this is a 2 pi r. This is about solenoids and toroids. We will discuss next topics in the next videos. Thank you.
Thank you viewers for your time. Don't forget to subscribe our channel and press the bell icon to get latest trending technology and academic related videos. For any further queries, please reach us at info@spjktechnosoft.com. Please like, share and subscribe our channel. Thank you and goodbye.